Okay, it's time to start our review of the sample test 3, approaches and comments. So let's get right into it. Problem number 1, basketball and golf ball moving towards each other. The balls collide head on. Well, that gives a pretty good hint to the type of problem it is. It's collision. And that means that we're going to have momentum conservation. If we read on, okay, weights, we'll put that in later. Elastic collision. That means we've got two equations, momentum conservation. Momentum conservation comes with this, and elastic means that we have kinetic energy conservation, or energy conservation. And we want to know the final speed of the golf ball. So let's get started here, put in some axes. If that's X, that's Y. Then this is going in the plus direction. And let's call this V capital B initial. This here would be V golf ball, so little g initial. And that's plus. And this is minus. So we need to put a minus on that there because it's going that way. That's kind of important to get this right away because for here, whenever you have a change in momentum impulse, anything like that, you want to get the pluses and minuses right. Otherwise, you'll run into trouble later on. So let's begin. This one here has a mass of capital M. A mass of the basketball is 5 times as much as the golf ball, so it's 5 times a little m. Little m is the mass of the golf ball. So if we write down momentum conservation, we'll start with the basketball. Big M times V basketball initial plus little m times V golf ball initial is equal to big M V basketball final plus little m V golf ball final. Okay, that's what we want. Let's simplify this, put in what we know. We get a 5m for this. Basketball initial is 2 meters per second. 5 little m times 2 meters per second plus m times minus 2 meters per second is equal to 5m V basketball final plus m V golf ball final. There's an m in every single one of these terms, so they all cancel out. And this simplifies, that's 10 minus 2 is 8. And it's equal to 5 V basketball final plus V golf ball final. So this is what we get from momentum conservation. From kinetic energy conservation in the head-on part here, that means 1D. So we use the simplified form. V, I guess we've been calling this V1 minus V2. So V basketball initial minus V golf ball initial is equal to V golf ball final minus V basketball final. Notice the switch in order, basketball, golf, golf, basketball. That's how that equation goes. And on this side here, that's plus 2, and that's a minus 2. Plus 2 minus minus 2. Those are both meters per second. That is equal to 4 meters per second is equal to V golf ball final minus V basketball final. Okay, so this is the equation we get for the other one. So we solve this for V basketball. We get V basketball is equal to the golf ball, let's see, move that to that side, move the 4 over here, minus 4 meters per second. Take and plug this into here. And so then you get 8 meters per second is equal to 5 times v golf ball, minus 5 times 4 minus 20 meters per second, plus v golf ball. And that tells us if we move the 20 over, we get 28 meters per second. Move that to that side. And this side, you have 6 times v golf ball. And if you divide 28 by 6, you get about 4 2/3. And 4 2/3 is that one. Okay, so this one was pretty easy to identify because we saw the collide head-on elastic, and then the algebra takes a bit of time. Okay, bicycle, 0.3 meter radius wheels, it's moving, so you have this angular speed, and so this here we can take as r, this here we can take as omega initial. If the bicyclist applies the brakes and the wheels slow with angular acceleration of this, hey, look at that, constant alpha. That gives us a pretty good idea of what we want here. In fact, it's minus 15 radians per second squared. How many revolutions? That's related to delta theta. So we have delta theta. We want delta theta. We have omega initial and alpha. Let's write them all down as we usually do. Delta theta that we want. Omega initial have omega alpha time. So we've got alpha before the bike stops. That says omega final is equal to 0. This is 0. I guess I can put in what they want. This one is 75 radians per second. And this one we don't care about. That's the minus 15 radians per second squared. So we go to the equation that does not have time in it. And if you remember the one that does not have time in it, goes something like this. It's the let's see, sorry. The omega v squared or omega squared minus omega naught squared is equal to 2 alpha delta theta. And let me just think a minute here. Yeah, that should work. And so let's plug into this. Omega squared is 0. Minus 75 squared radians squared per second squared is equal to 2 times minus 15 is minus 30 radians per second squared times delta theta. So delta theta is then equal to, minuses go, 75 squared over 30 radians. We want revolutions. There is 2 pi radians per revolution. Radians cancel out. We do the multiplication and we get that there's
about 30 revolutions to this. This is about 6. Well, 75 squared is, well, this is 3 times 25. So one of them goes, you get 25 times 75. They take pi for the other 3, and you get, I guess, 25 times 25 over 2 over 20. And so that's going to be a little bit over 25. Yes, it is. Okay, number 3. Okay, so again, you're given an angular acceleration. It's constant. You're talking about how far. It's a pretty easy one to see. There's no time in it, which is another indicator of those, but it's pretty good. Okay, Tim attaches a string to a yo-yo to his finger, releases from rest. That's probably important. As the yo-yo is spin down, keeps his finger motionless. The yo-yo is treated as the same as a freely rolling object. Drops a distance, translational speed, or angular speed. Okay, and the air resistance and friction are negligible. So we're given a drop. We're given an initial and a final, and we're given speeds, or asked for a given. Those kind of hint that we're talking about an energy problem. And so let's write down what we always write for energy work non-conserving is delta KE translational plus delta KE rotational plus delta PE gravity. There's no spring here. I won't bother putting that on. This is equal to 0 because of that. And it starts from rest. That means KE initial is equal to 0. So I only have to write down the final KE. So I get 0 is equal to 1/2 mv squared. Our final speed is 4 meters per second plus 1/2 I omega squared. My final omega is right there. Now my potential energy, I've lost it. I'm going down, so it's going to be negative mgh. So what do we have? 0.1 kilogram yo-yo. V I've got is up here. I is what I want. Omega is 180. So omega squared is 180 squared radians squared per second squared. M is again 0.1 kilogram. G is our friend 9.8 meters per second squared. H is 0.9 meters. And so I've got everything in this equation except I. So solve for I. The rest is numbers. So you can almost stick it in your calculator, and the answer you get is this one. So that's number 3. Again, once you pick it off as an energy problem and you start seeing you've got all the numbers you want, you're pretty convinced that that's how you should stay. Okay, Kathy is 25 meters from a train when it blows the whistle. And the sound intensity, well, that kind of gives us a hint of what kind of problem it might be. And we want the power of the sound emitted. So we're already thinking in terms of power is equal to intensity times area. That's what we want. Intensity, we're going to have to convert from dB. And area is equal in all directions. So that's going to be pi, or 4 pi r squared, where r is the radius, 25 meters. So if we wanted to plug into this,
if we want, we're given I in dB, so we want to go dBs to power. And so to do that, we're going to use our inverse. So we use I is equal to I naught e to the minus e to the plus beta over 10. And beta is our dB value here. And I naught is 1e 12 plus 12 watts per meter squared. So if we stick this in, the I naught 1e 12 watts per meter squared. And this is not e, this is actually 10. And it's 10 to the power 80 divided by 10 is 8. So that's 10 to the, it is minus 12 here. So it's 10 to the 8th minus 12, 10 minus 4 for this part so far. And then we have to put in the area of 4 pi 25 meters squared. And now it's simply a multiplication. If you do the multiplication out, you'll get this one. Right, this gives you, right, those two I said give 10 minus 4. 25 squared is 625. And that's a little shy of 1,000. So it's like 10 minus 1. Pi times 4 is going to be more than 10, but not by too much. So this is actually looks just about right. When you put it in your calculator, you'll know that that's the right one. Okay, this one was what we call a definition type problem, because you just pull out that definition, put in the numbers, a couple other useful results to get there on the way. You'll use this one a lot. So that's the inverse of the one that you normally find in the book. Make sure you have that one written down. I naught 10 to the beta over 10. I is equal to I naught 10 to the beta over 10. Beta is the dB. I naught is 1e minus 12 watts per meter squared. And there you can actually see it. Okay, that's our page 1. Now we go to number 5. Simple pendulum. I'll say to the frequency. Frequency is F equals 34 cycles per minute. That's an odd thing. If the length of the pendulum is increased by 4 times, what is the new frequency? Okay, so to do this one, we need to know what the frequency of a pendulum looks like. And so there's a formula for that. The omega for a pendulum, we know is equal to the square root of g over L. And we also know that omega is equal to 2 pi f. So the frequency of a pendulum is 1 over 2 pi, the square root of g over L. Now, whenever you see, we're not given what L is. So the best thing to do now is to say F initial is equal to 1 over 2 pi, the square root of g over L. And F final is equal to 1 over 2 pi, the square root of g over 4L, right? Increased 4 times. Now, we can pull the 4 out of the square root, right? it comes out as a 1/2 because it's a square root. And this is equal to 1/2 times F initial, right? Because once you pull the half out, right, it's 4 inside, pull out a square root, it's 2 at the bottom. Then you get exactly this, what's left over after the half, and so it's a 1/2 F initial. So the new frequency had better be 1/2 of 34, which is, of course, 17 cycles per minute. Can't write hertz because it isn't. Number 6. A volleyball pole is shown here. Exerts a net force 120 newtons to the left, 1.8 meters above the ground. Support wire is attached 2.5 meters at 54 degrees. Assuming that the ground does not apply a torque to the pole, what's the tension in the cable? Okay, so we're assuming there's sort of a loose hinge down here. So we're talking about statics here. That's Newton's second law. And we know how to solve that one. We have to make our chart, force, and I'm going to make little thin XY columns because we're not going to use them. Leave torque wide here, right? Torque generally is RF sine phi. So we better draw a little free body diagram. Let's draw it for the post. We have to decide where we're going to put the axis, right? So let's do X and Y as usual. And let's put the axis right here. And there's a reason why we do it, of course, and that's because we don't know the forces there. So if we put those axis forces here, we have reaction forces in here. Reaction forces act right at this point, so they give us 0 torque. Then we have F, which gives us over here, it's 100. Well, first it's trying to go this way. That's plus. R is 1.8 meters. F, 120 newtons. And phi is 90 degrees. You can use either 90. Sine of 90 degrees. Degrees means the calculator has to be in degrees mode. Sine of 90 degrees happens to be 1. And what else we have is the tension. And the tension is this way. It's pulling down like that. And it's going to be minus because it's going down this way. If this is 54 degrees, then this angle up here is equal to 90 minus 54, which is, that would be 36 degrees, right? And so, because we need, remember, you want the angle from here to there. That one is irrelevant. You take either this one or you take the one over there. We're going to take this one. Easier. We have it. And minus, this is now 2.5 meters. Tension force, we don't know. That's what we want. We put it as a letter. And the sine here is 36 degrees. So if we sum these up, we get torque net is equal to I alpha is equal to 0 because it is static. And if you plug these in here, then I guess I didn't use this, did I? Well, anyway, we had the tension up here. We had the force over here. This is 36 degrees. That is, what is it, 2.5 meters. This over here is 1.8 meters. and 120 newtons. And this is our axis and unknown forces. Fill that out. We actually pulled off this one, which is often worthwhile. So if we solve this thing here, that's plus, that's minus, they're equal to each other because it's 0. So I get the tension is equal to the 1.8 meters, 120 newtons divided by 2.5 meters times the sine of 36 degrees. Plug it into your calculator and you get 147 newtons. Okay, once you see its statics, which of course you have forces, nothing's moving, you immediately have Newton's numbers 2, and you know that AX equals AY equals alpha is 0, because it isn't moving, it doesn't start to move. Okay, displacement versus time looks like this. 2 kilogram mass on a spring, position versus time, that's clearly oscillations. Oscillations make you think of that formula we have. We want to know the spring constant K. Well, what do we know for the spring mass on a spring, omega? But we don't know omega. This is time here. So it means from here to here is 1 period. And if we actually calculate out, that's 0.4 minus 0. Goes 0.4 seconds. Now, if we look at the formula for the period of a spring, T spring is equal to 2 pi square root of m over k. You might say, I'm used to square root of k over m. That's because the period goes 1 over the omega, and omega is square root of k over m. The 2 pi comes from the fact that this is related to frequency in hertz, not omega. Okay, so we know T, we know 2 pi, we know m. What we don't know is k. So we divide both sides by 2 pi, square it. Actually, it's better to, well, we want k by itself. So we really want to multiply both sides. Why don't we square everything and then multiply by k? So t squared is 2 pi squared m over k. Then you multiply by k and you divide by t. And you find that k is equal to 4 pi squared times m divided by t squared. Right, because if I square everything and I divide by t and multiply by k, those are the only things that aren't squared, and that's where they belong. I can then plug and chug, and the answer to this is this one. That's another formula-based one, but again, you've got to be able to read the graph. Again, there was 3 types of problems. One of them is to read a graph, get a number. We also had to use a definition here. And move on to the next one. So we have 4 kilogram mass oscillates in a spring, the spring constant, position versus position amplitude is this. What is the speed when its displacement is 0.25 meters? Okay, so let's go write down what these things are. We get a spring constant in this, so we can get omega is equal to the square root of k over m. That's going to be the square root of 210 newtons per meter over 4 kilograms. So that's the square root of, well, you can solve for that. Position amplitude is A, is equal to 0.45 meters. And we want the speed when its displacement is 0.25 meters. So we're going to need two equations here. We're going to need the displacement equation, x is equal to a cosine omega t. We might as well take this to be time to be 0 when we want, because we'll pick off the time from this. And we'll set the velocity is minus a omega sine omega t. So that's what we're going to need. So we're going to solve this for t. And then we're going to put it in here. Because we have a, we have omega, we'll get, we have this x, right, it's this. And we have this, we can work this backwards, right? So the, if we take the, solving the top one there for t, you have t is equal to 1 over omega times the arc, okay, the, oh yes, times the arc cosine of x over a. Because you divide this, take the arc cosine to both sides, and then you have to omega t, divide by the omega, you get this. And remember, this is a trig function. You want radians mode. That'll give you t, and then you're going to take that t and plug it right back into this one to get v. And if you go through and work that out, you will get answer C. Now speed, remember, is always positive, and so all these answers are positive. If we get a negative, we'll just take the positive out. When you're running this backwards here, you also need radians mode in there because omega gives you radians. Okay, that is 8. Now we go on to 9. Bullets shot into a block of wood, a string. Comes embedded in the block of wood. Oh, embedded, huh? Embedded means sticks together. That means it's a perfectly elastic collision. With V finals the same. Momentum conserved. Okay, and it swings up, and we want to know how high vertically does it go? Well, the collision is only going to get us to here. This is our V final. So the collision goes from initial to final. It doesn't get us up to H. So then we're going to have to take this as an initial for the energy, because whatever, we're moving now, we're swinging up, we stop. That's a classic energy problem. And so this will be the final for the energy part. And so we got 2 steps. This is energy. So the first thing we do is find this V final, and then we go through an energy problem to find that. So it's a 2-step problem. Okay, because how high vertically, that's, and we're starting, we'll get a speed out of this. And so that's how we get the idea of energy conservation. So let's start with the collision. It is momentum conservation. And so we have, let's see, we got a bullet and a block. So let's call the bullet little b and the block big B. And momentum conservation goes like this. Mass of the bullet, V of the bullet initial is equal to, plus mass of the block, the block initial is equal to the sum of their masses times the final. And initially, the block isn't moving. And so you get V final here is the mass of the bullet, V bullet over the sum of the masses. And this, if you look back here, we've got the two masses, we've got the bullet initial, and so this gives us a number. Now we go to the energy. At the start, we have a KE initial equals 1/2 mv squared, where this is the V. I won't write the F on it because it's initial for this problem. And at the end, KE final is equal to 0. At the start, potential energy of gravity is equal to 0. At the end, potential energy of gravity is equal to mgh. Capital M, which is the two of them together, M bullet. This is also capital M. M bullet plus M block. Right, they're both together here. GH. Now, if you neglected the bullet, it probably isn't going to make a whole lot of difference. This doesn't weigh much. And work, let's write down our formula. Work non-conserving, it's equal to delta KE plus delta PE. This is going to be 0 because nobody told us about friction. I think it said neglect air resistance. That's where it comes from. About the only place we can come here. And of course, this means, generally speaking, KE initial is going to equal PE final once you put all the pieces in of what's 0. And so you get 1/2 mv squared. All that's known is equal to mgh. The m's actually cancel out, and you get the height is equal to little g v squared over 2. We have v, we get g, we get 2, we get the height, and the answer is A. Right up here. Number 10. 2 solid rods, each of length and radius, are connected together as shown. This. When they're rotated about the horizontal axis, this one, what is the equation for the moment of inertia? Well, I'm going to add them up, right? I is equal to I1 plus I2. Let's make this one here 1 and this one here 2. And if you look at this picture, this is 1 and this one is 2, because that's about the center and that's through the middle of it. Neither one is about the end. And so that's equal to This one is mr squared over 2. And this one is where are we? 1/12 ml squared. And so we can get an answer for this one. That is this. Wasn't too bad. Notice how we give you the moments of inertia. That's how we do this. Okay, Hank shakes a rope, creates a transverse wave. Distance between the crests is this. A new crest reaches every 0.4 seconds. What's the propagation speed of the waves? Well, what are these things here? The distance between wave crests is this. What is that distance between wave crests? That's the wavelength. And new crest reaches the end every 0.4 seconds. That's the period. So this is the equation I'm sure you remember, V equals F lambda. And F is, of course, 1 over T. And so 0.5 meters divided by 0.4 seconds. You get meters per second. And 0.5 divided by 0.4 is 1.25, which this is the closest to. Ice skater spins with arms tight against her body, which isn't like it is in the picture. She has a moment of inertia. This, and angular speed of that. She stretches her arms out. There is the final picture. And new angular speed slows to this. What is a new moment of inertia? Well, what we see is I changes. There's not too much description. And both omega and I change. That means it's probably a collision. It's rotation. So L is conserved. And so we write I initial omega initial is equal to I final omega final. And we want to know I final. It's equal to omega initial over omega final times I initial. And we can write those down. The initial one was 15. The final one is 6. And this is 1.2. Those units cancel. Kilogram meter squareds. So 12 divided by 6, this is 0.2. 0.2 times 15 is 1/2 times 2 is usually pretty close to 3. And so the answer should be A. Drawbridge, shown in the figure below, has a mass and a length. So we can put that on the figure. That's 30 meters. Center mass with the span is this geometric center. Span pivots freely at the base. It's supported by a cable attached 10 meters from the pivot. Span is raised 37 degrees above horizontal. Cable becomes perpendicular to the span. That's 90 degrees. What is the tension in the cable when the span is in this position? Well, this looks like statics. So that's Newton's number 2. Alpha equals 0. So we've got this is 30 meters, then 15 meters along. We've got the weight going down. And so the angle in here is 90 degrees minus 37 degrees, which is 53 degrees. This angle doesn't matter for the calculating torque of omega, that one does. This angle matters from torque due to the tension. And so if we do torque net is equal to, I could do this with we could use a table, but it isn't too much. We choose the axis at the axis of which pivoting on, and then we have the torque due to the tension, which is this way. That's going to be a positive torque plus the torque due to the weight. That's going to be a negative torque. And so this is equal to 0. And the tension is equal to 10 meters. R. F is the T. Sine of 90 degrees. It's going to be 1 minus, because this is going this way, that's minus 15 meters. And the weight here is mg, and it's times the sine of 53 degrees. That's degrees. Use degrees mode. M and G we know from that. And so the only thing unknown in here is T. And so if you go through here and chunk the numbers into your calculator, you get this one. Okay, so 14, speed of sound is 0 to C, 0 degrees C is 331 meters per second. If the speed propagates at 331 meters per second, what is the air temperature? Well, we pull out our handy dandy formula. This is just a definition. And it says that V sound is equal to 331 meters per second, the square root of temperature divided in Kelvin, divided by 273. And so this is equal to 341. So we get 341 over 331. We square that. We multiply by 273, and that's equal to, and that's T in Kelvin. And so what we have to do to get it in C is we have to subtract off 273 Kelvin is equal to T in degrees C. And you can then chunk in the answer and you get 16.7. That number is bigger than 1. So this will be bigger than that term, so it should be positive. So you know it's one of those two. Your calculator tells you which one it is. A few more to go here. Child of the swing with a small amplitude, so its motion is simple harmonic. Period of 6.3 seconds, that's T. What is the length of the swing? Okay, it's a pendulum, and it's a definition. The period of the pendulum, you can look up in your formula sheet. If you have omega, then you just convert omega to frequency, and 1 over the frequency is the period. and it's 2 pi square root of L over G. We want L, so we divide by 2 pi, we square it, multiply by G. So L is equal to G times T over 2 pi squared. It's a plug-in problem at this point. And the plug-in problem here tells us the answer is this. We've got a spacecraft here on number 16. X direction this much, and an asteroid moving the Y direction with a speed looks like that, and they're on a collision course. When they collide, the asteroid becomes embedded in the spacecraft. That's what's unfortunate. What direction is best described with the aircraft embedded, moving immediately after collision? So embedded, that sticks, perfectly elastic. And so we have momentum conservation. We have here both X and Y. And so what you, if we look at our picture, the spacecraft, fins on it, I guess. It's moving in the X direction, and the asteroid is moving in the Y direction. That's asteroid, and that's the spaceship. And then they hit and go off in some direction, the final. And that has X and Y. So if we write the X equation, we write mass, the spaceship, the X, the spaceship, plus mass of the asteroid. The X of the asteroid is equal to their sum, the final X, that's 0, that we have, we can solve for Vx. In the Y direction, mass Vy satellite plus mass asteroid Vy asteroid is equal to mass, there's sum, the final asteroid. That's 0, have that, have those, get this. Then we want to know the direction, and it's counterclockwise and positive x-axis. So that's an arctangent. And so angle is equal to tangent minus 1 of the y part. The final, this is y. Y over the final x. That gives you this, because if you draw a little picture, it's somewhere here. There's our angle theta. So y over here and x over there. So the arctangent is y over x. And so you then just comes a plug-in problem. And if you plug in, you get 10.7 degrees. Notice the degrees here. Calculator. It's a trig function, or an inverse one, in degrees. Okay. Tennis ball dropped, bounced off the floor, and it returns to this height. How much energy was lost in the collision? Energy is lost. That's work non-conserving. Work non-conserving is equal to delta KE plus delta PE. If we look at this, dropped KE initial is equal to 0, returns to a height, so the KE final is equal to 0. And so this is PE final minus PE initial, which is mgy final minus mgy initial. And there's m, that's y initial, that's y final. So y final is less than y initial, so you get a negative. Negative is because it's loss. So I'll just take the positive part because the loss already has the negative built into it. So it's a matter of just plugging in with the known mass, and G we know, Y's. And if you do that, you find that it's answer C. You know, whenever you see different heights, energy lost, that's a good hint. Potential energy change usually comes into energy formulas. Okay, lifting arm of a crane goes 250 meters. There it is. And 450 kilogram ball is off the end of the arm. The wrecking ball is motionless and is 22 meters horizontally from the base of the crane. Then what's the magnitude of the torque about the base of the crane? Well, we can ignore the mass of the crane's arm. Yeah, sure, but it's 211. What do you expect? So in order to get the torque, we need R F sine phi. Well, this isn't too bad. R, the torque arm, is 250 meters. Force is mg. We need to know what the sine of phi is. Well, that's phi right there, right? So if we bring down this little triangle, we've got 250 meters this way, we've got 22 meters this way, and that's to the base, so that's 90 degrees. There's phi. We can use either this phi or that phi. We'll use this one because it's in our picture and it's in our triangle. And so if you look at this, the sine of phi is equal to opposite over hypotenuse, which is 22 over 250. And so we just plug right that in, 22 over 250. And G, of course, is 9.8 meters per second squared. M is our big 450 kilograms. And this is now something that you can just calculate. It's that times 22 because 250s cancel. And then plugging that in, then you get C. That's a simple definition as well. These are supposed to be the easy ones, they're just definitions. Okay, bicycle slowing down. The wheels slow with an angular acceleration of this. Again, looks like constant alpha. So we use kinematics. kinematics. Wait a minute. It's not kinematics. Each wheel has a mass of this. What is the net torque? Oh, that's something interesting. Forget kinematics. We want net torque. Torque net is equal to I times alpha. See, that's a case when you look at it, you say, it's constant accelerator, I'll use kinematics. And then you read down, you say, well, wait a minute. I was about to write these equations down, realize it didn't tell me all the other stuff I needed. It tells me I want net torque. Okay, that's Newton number 2. And, okay. It looks like the only thing that we need is well, they're the same. 2 times I, one wheel, alpha. And I, one wheel, you're supposed to use mr squared. So it's 2 mr squared alpha. And now it's a matter of 2 times 0.4 kilograms, 0.3, so 0.09 meters squares. Alpha is minus 15, 1 over second squared. The radian we can drop. You start multiplying those things out. The minus sign is going to come through, and you're going to get this answer when you're done with your calculator. Last one. What do you know? 1.5 kilogram mass is suspended from a spring motionless. That's interesting. Not a vibration problem. Spring extends this far. If the mass is pulled an additional 1.2 centimeters and release, what's the maximum acceleration? Okay. Maximum acceleration. It's pulled an additional and released. Okay, so what we're doing is we're starting an oscillator of a spring mass. And so the acceleration here, if you go pick up your oscillator formula, is minus a omega squared. Now it starts at the maximum distance with no velocity, so its phi is equal to 0. Max x v equals 0. That tells us that phi is equal to 0. And so this is cosine of omega t. This is A max. A is 1.2 centimeters. It's equal to 0.012 meters. That's that. We need omega. Square root of k over m. We've got m. We don't have k. So we need k. Now we don't give up. We say, okay, let's look at this as a new problem. And we see suspended motionless and extends this far. Looks like statics. So here's our spring. There's our mass. And we have a force going upward. F spring is equal to Kx is equal to K times 2 centimeters. And we have a force down, W is equal to mg. And so this isn't moving, it's statics. So F net is equal to 0. Statics is equal to Kx minus mg. So K is equal to, move that to the other side, mg over x. So we get K this way, we shove it in there, we have the mass, we get omega, we have A, we plug them into there. If you go through all of that rigmarole, you end up with, which is just calculator work, you end up with answer A. And that's just about it, because that is the last of our problems on the test. I hope that you did well. I hope this helps if you didn't. And I hope you get these hints for how to start. If you had trouble starting, look at how I did it, think about it. How would you think of that? Okay, good luck on that test. And we're ready to stop.